doing proofs basically since lesson 6.1. And I've been giving you guys 4 corners, and we've been working with proofs. Now in this lesson, the only thing that makes it a little bit trickier is the fact that we are going to extend past just the top part of the formula sheet, and your proofs can now include anything that's on the right-hand side of the formula sheet, except for the arc length formula and the sine and cosine function formula. So double angles can now find themselves inside the proof. Okay. Remember, we don't always default to sines and coses right away. We do not want to do that. What we want to think about is okay, how can I make really smart decisions based on this formula sheet? When you can't make a substitution or a clear substitution that makes sense to you, then you might start looking at double angle form. So make sure you're defining your left side as it is and your right side as it is. Okay? And you do not work on the first step. The next step is where you begin your work. Okay? Now I'm going to show you the most common mistake people make. How did I break math when I bring the exponent into a binomial? What math did I just break? When you're squaring a binomial, it requires binomial expansion. And in grade 10, you guys referred to it as FOIL because that was the mnemonic device, right? You can't bring an exponent into a binomial because of the addition and subtraction sign. We could have done this, like if I had 2 tan x all squared, then that would have been 4 tan squared x, because technically we're multiplying it by itself. But as soon as you see addition or subtraction, we need binomial distribution. So when I start looking at the binomial distribution here, I've got tan squared x, and then I've got minus tan x. This is not a difference of squares, so the middle terms stay, minus tan x, and then a negative times a negative is a positive 1. And when I put my like terms together, okay, resist the urge to change to sines and coses. Just resist it. I'm serious. And the reason why is because I see a connection between sec and tangent. Is there a formula that connects secant with tangent when it's in the squared capacity? Like as soon as you see squareds, you have to recognize that there's a Pythagorean substitution that might be handy here. Now notice, I've got the negative 2 tan x that I needed on the right side. I've got it right here. Did you guys see that? So all I'm going to do is I'm using my right side to guide my thinking on the left side. So I've got tan squared x plus 1 minus 2 tan x. Leave it there. Where have you seen this before? Look at your formula sheet. There is a relationship between secant and tangent. What is the relationship between when they're squareds and they've got 1s? Right? As soon as you see 1s and squareds, we're looking at the Pythagorean identities. Do you guys see that tan squared x plus 1 would be sec squared x minus 2 tan x? And now my left side equals my right side? Do you guys see that? You would have opened up a massive can of worms that you can't put back if you would have gone straight to sines and coses. So what happens when I see a sec squared like this connected to a tangent? I'm going to go to my formula sheet. I'm like, I think that those two are connected somehow. And then that's going to be the thinking that you're going to keep with you for the duration of the proof. Okay? Anyone most common mistake people make is they bring the squared in. They call it tan squared x plus 1. And then they'll say sec squared x, and they've got no idea where this comes from. Okay? That would be the most common mistake there. Okay, let's take a look at the next one. Okay, so if we're going to do the proof, define your left side, define your right side. Your first step, you do not, and I'm going to leave lots of room on the right hand or left hand side here. Okay, so define your left side, define your right side, tan x. So right away I'm like, there's no squares. There's no squares anywhere, which means I'm probably not going to be doing a nice, neat Pythagorean substitution. Is there anything that connects to a double angle formula or a sum or difference formula? Not at all. Because it doesn't connect to Pythagorean substitution, because I don't see any connection to a double angle or a sum or difference, then, so I first define my left side, I've defined my right side, and all of those strategies have kind of like, okay, I don't have a quick substitution that I can do, then I'm going to go sines and coses. I don't see squares with those ones. Because I don't see the squares with the ones, I might work on the right side as sine x over cos x. And then on this side, you need to put brackets around your numerator. And brackets around your denominator. Because we can't multiply by the reciprocal until we have a single fraction on the top and a single fraction on the bottom. So guys, find a common denominator. So this would be like cos x over cos x. Are you guys okay with that one? And then this one becomes sine x over sine x. Just that, you have to, like, so these brackets first, right? Ed maths, right? We got to figure out one single fraction for those brackets first. So what happens on the top there? What is this numerator going to become? Do you guys see that that's going to be cos x plus sine x? Still a binomial, and then it's divided by cos x. The denominator just stays the same. Like, it's not two, like, it's just, this is just cos x plus sine x. The denominator's the same. It comes along for the ride. Now, I'm just going to make a bold move because I don't like my stacked fractions. I'm going to get my single fraction here, which is sine x plus cos x all over sine x. So if you want to just avoid the stacked fraction situation, then just make sure you've got your brackets around your binomials. Guys, does order matter for addition? Is 3 plus 4 the same as 4 plus 3? It's the same. So order doesn't matter for addition. So when I multiply by my reciprocal, this, you can't take terms, like I can't take this cos x with this cos x, right? Like, you can't do that. You have to take a full binomial factor, can divide a full binomial factor. I'm left with sine x over cos x, and left side equals right side. I'm going to use the same skills of having to find a common denominator. And again, like, you have to constantly be thinking about your order of operations. Do you see squares anywhere? Do you see anything that might connect to a double angle formula? You got to look for the path of least resistance first, and if you don't see anything that looks like a double angle formula or a sum or difference formula, then you go to sines and coses, okay? Now, did you guys recognize that this is 1 over cos x divided by sine x? minus sine x over cos x. Order of operation dictates we have to do division before we can do the subtraction. You are not finding a common denominator yet. You have to get a single fraction here. We have to do this division. So what's 1 over cos x divided by sine x? Like, what would that become? When you multiply by the reciprocal, the sine x joins the bottom, right? It becomes 1 over sine x. Do you guys see that this becomes 1 over cos x times sine x? Most common mistake, people somehow think that when they're dividing by sine x, it goes to the top here. That's not the way that works. Right? Like, just connect it to your junior high skills. You guys know how to divide fractions. Just do the division. 1 over cos x divided by sine x becomes multiplying by the reciprocal. Multiply straight across top, straight across the bottom. Now, how am I going to find a common denominator? What's your gut telling you to do, Leo?
Times the other side by sine x.
Absolutely, top and bottom. Now, guys, you have to, I'm just going to give myself a little bit more room. You have to show that, okay, this was cos x sine x. And guys, you're never going to have a proof where left side doesn't equal right side. If you are like trying to force an issue and it's like you're not getting it, you've made a mistake. Go back and find where you broke math. And so what Bulio is saying is he's like, hey, my denominator is cos x times sine x. This guy, I need to multiply top and bottom. I have to show that I multiplied top and bottom by sine x here. And then we write the common denominator just once. So cos x sine x. And then on the top, I get 1 minus sine squared x. Guys, where have you seen 1 minus sine squared x before? What makes you think that, oh, I need to look at my formula sheet? Like, you guys get that this is cos squared x, right? So this is where you would recognize that Pythagorean substitution. Okay, here's a common mistake people make. Why is this wrong? This is a binomial. You cannot take a factor from a term. You can't do that. On top, this is a binomial. The only thing you can do with a binomial is you can factor it, or you can do a Pythagorean substitution to turn it into a monomial. Once everything is multiplication and division, then you start dividing common factors. So this becomes cos squared x. Now that you don't see any more addition and subtraction, okay, this cos x divides this cos x, and we get our cotan x. Left side equals right side. So you have to ask yourself, like, where are you breaking math? Like, what rule do you consistently tend to break? Because all of your math skills come into play. And that's why this unit is really tricky. And it's just more practice for these identities. So keep on working. Now remember, this line is a grouping symbol. So when you're going to approach this question, you're going to have to get a single fraction on the top and a single fraction on the bottom before you can multiply by the reciprocal. entry-level marks, I would have worked on the right side first. Like, that would have been mine. And there's no Pythagorean substitutions. There's nothing that, like, jumps out at me there. And you are still using your formula sheet consistently whenever you're doing those substitutions. Guys, when I multiply, this already has a common denominator. When you write this as a single fraction, what does this become as a single fraction? Yeah, people are ditching the 1 plus. The 1 plus matters. It's super important. So I got 1 plus cos x over sine x, and this is my whole top as a single fraction. What do I have to do to the bottom? Times by cos x, top and bottom. Now this is the part that really troubles people. Okay, so this is the conversation I often have. When it's a binomial, we look to factor it, or we look for a Pythagorean substitution. Well, what do you guys do here? When you see the binomial on the bottom, what do you see as a strategy moving forward? Yeah. Do you guys see that you can factor out a GCF? Okay, so there was no Pythagorean substitution. So if I factor out a GCF, and I'm going to turn this into a division statement where it's clear. So I'm dividing by, when I factor out the sine x, I'm left with 1 plus cos x. If you didn't see that GCF, you're going to just like, you're going to try to do things that are going to cause you to break math. You had to recognize the need to factor here. This is a standard of excellence because it's got all the stacked fractions. Now when you multiply by the reciprocal, factors divide factors. Explain to me, why can I not do this? Because people do it all the time. Why was it wrong back here to divide this cos x by this cos x? Yeah, that's part of a term. But we're not, but now, okay, so now that we're here and everything is attached, like, and I'm not taking a piece of something, I'm taking the whole factor with the whole factor, and it doesn't get harder than this guy. Except for when you use conjugates. That gets tricky. Again, try to get one step ahead of me. Can I just talk to you guys just for a second about your quiz? It just dawned on me right now, and I don't want to forget. Okay. Did you guys try this one? I'm going to give you guys a minute to get ahead of me. You're thinking single fraction on the top, single fraction on the bottom. guys recognize that this one used the same skill as the last one? Like recognizing the need to kick out a GCF? Did you guys catch that? Oh, I'm sorry. No, I just want to make sure I'm making my computer, or else I'm going to start coughing. Oh. I'm not upset about the fact that you moved that chair. Okay? Did I just move it back in front of you? Okay. Now, you have to carry that denominator with you. If your work doesn't flow for me, I can't give you the marks. And it's always a left side, right side. So don't just do like, oh, I'm going to do this my own way, and I'm going to hope that the marker, like, understands my thought process. But guys, did you recognize, what do you do with a binomial? Either it's got to be a Pythagorean substitution, which it isn't, or we start factoring, right? And so when you factor out that sine x, what are you left with? Cos x plus 1, right? So now I'm just going to write this as sine x cos x plus 1 all over cos x. Now, this is not a fraction, but when you multiply by the reciprocal, it goes to the bottom. And you guys have to be careful with this step here. This was not a fraction, it was just cos x plus 1. And then when you multiply by the reciprocal, then we get to divide common factors. Sine x over cos x. Write it out one last time. That's what I turned the right side into, so left side equals right side. So, when you have a binomial, you look for a Pythagorean substitution. If it's not there, you look for opportunities for factoring. Yeah? Okay, guys, try this one. Oh, we're verifying. Woo! We like a verify. Verify is not a proof. Verify is telling you to substitute the angle measure in, and then you have to find all of the ratios for that angle measure. So, still define your left side. Still define your right side. Substitute the angle in. Guys, when it's a verification, you do not change your cosecant to sine. You do not change your tangent to sine over cos. You do not change your secant to 1 over cos. You figure out what secant 30 was. You figure out what tan 30 is. You figure out what cosecant 30 is. So this is coming back to your chapter 4 skills. So when I dive into this question, I'm just going to do a quick little like 30-degree diagram right here. And I know it's root 3 over 2 and 1/2, which means cosecant is the reciprocal of sine. So cosecant 30 degrees is 2. So I get to put a 2 here, minus tan of 30 degrees is the y value divided by the x value, which gives me 1 over root 3. Now, if you want to just rationalize at the end, you can. If you want to leave the radical on the bottom for now, you can. If you want to rationalize now, you can. I'm just gonna choose to rationalize now. And if you rationalize on one side, just make sure you rationalize on the other side too. And then secant 30. So secant 30 degrees is the reciprocal of cos, so 2 over root 3. And when I rationalize, I get 2 root 3 over 3. Are there any more trig ratios that I need for this? No. Okay. So I've got everything that I need. I'm just going to use a different color here. So my cosecant 30 is 2 minus tan of 30 is root 3 over 3 times secant 30, which is 2 root 3 all over 3. When I go to the right side, cosecant 30 is 2, so this becomes 2 squared, times tan 30 is root 3 over 3, all squared. So what people were doing on the quiz was that it was a verification, and then they did a proof, they proved it, and then they did the substitution. And that's not how you approach verification, okay? So, board of operation dictates, guys, what would root 3 times 2 root 3 become? So it's going to be 2, what's root 3 times root 3? Like, if you multiplied straight across the top, what's root 3 times? This would be 2 times 3. Do you guys see that it becomes 6? We multiply coefficients by coefficients, radicands by radicands. So technically, this is like 2 square root 9. Well, what's the square root of 9? It's 3. Root 3 times root 3 is 3. So then I get 2 minus 6 over 9. You could type that into your calculator right now if you want. Or else it's 2 minus 2 thirds, which gives you 4 thirds. Is this would have been 6 over 3. 6 over 3 minus 2. So this just becomes 4 thirds on the left. But you can let your calculator do the work. And guys, if you see a root 3 times a root 3, you probably could have let your calculator do the work here, but this is really nice to show this intermediate step if you wanted to get full marks. Like just, if you typed this into your calculator as separate fractions and you're not sure, like maybe my radical skills are really like kind of rusty, as soon as you see root 3's that are getting multiplied, the radical is going to be gone. So I've got root 3 divided by 3. There's my first one, times bracket 2 root 3 divided by 3. And when I math fraction that, oh, where did I go wrong? Root 3 over 3 times 2 root 3 over 3. 3 times 3 is 9. Oh, because I didn't do the minus 2. Oh my gosh, this reduces to 2 thirds. It is 2 thirds. 6/9 is 2 thirds. And then 2 minus that answer. Oh my gosh, math fraction that, right? But this is radical work from grade 10 or grade 11, right? We know that 2 squared is 4. Root 3 squared would be 3 all over 9. So this becomes 12 over 9. What does 12 over 9 simplify to become? 4 thirds. Left side equals right side. Are you guys okay with this whole process of verifying?
Do you simplify all the way to get full marks?
If as long as they match.
You got 12 over 9 and 12 over 9.
If you got 12 over 9 here and 12 over 9 here, then it matches. That's all that matters. Like, as long as your left side equals your right side. Yeah. Okay? Bugs me, but it's not wrong. Okay, guys, give me this explanation. Explain why a verification does not prove an identity. Okay, so this is probably where I'd begin. A verification is true for that value only. It's specific to the value indicated. And then I would say it is not a proof for all possible angle measures. For example, and I'm just going to do the quick example, theta equals 30 degrees. The verification is just specific to 30 degrees and not necessarily a universal proof. Like, remember on the first page of chapter 6, we said an example does not prove an identity, and all it takes is one counterexample and it's no longer an identity, right? But a single example does not prove an identity. If we wanted to do a proof on this, we would have had to go thetas, and we would have had to manipulate the left side and the right side to be equal for all possible angle measures. As soon as you do a verification, it's only specific to that angle measure. Does that look okay? So this is homework I'm going to check on Monday. Okay, I'm going to post the 10-a-week answers. We're going to finish. So on this last bit, we're now going to solve trig equations that are going to have double angles in them. And we're going to have to do a substitution from chapter 6 to solve the trig equations. But we will finish lesson 6.4 on Monday because your quiz is going to be short and sweet. And if you want the extra 15 minutes, you can. Okay? So you know what, why don't you guys pack up? I'll make sure I post that 10-week solution. So pack up. Everyone got the 10-a-week yesterday, right? Okay. Pack up and let's go to the whiteboards for just one quick proof.